All right, it's time for our second segment of the Class 3 lecture, and we'll be talking about the components of atoms, the subatomic particles that make up atoms. There we go. So there are three main subatomic particles that we want to be thinking about: the electron, the proton, and the neutron. Protons and neutrons actually are made of more fundamental particles, quarks, but we're not quarks, gluons. We're not going to get into any of that because none of those particles are accessible through chemical reactions. So they're really irrelevant to what we're doing now. We can treat these as the fundamental building blocks. So I've got electron, symbol E, proton P, neutron N. And so if we look at the masses, we see that a proton and a neutron have almost exactly the same mass, a little bit different, little off. But the big difference is a neutron has zero mass, whereas, zero charge, whereas a proton has +1 charge. An electron is much lighter than a proton or a neutron. Its mass is about, a proton is about 2,000 times heavier than an electron. But the biggest, so that's one big difference. The other big difference is that the charge is -1. And because the charge is -1, it means that electrons and protons are attracted to each other. Whereas protons are actually repelled. How can they be packed in the nucleus? Well, that's because the strong nuclear charge, which is much, much stronger than the electric charges, than the electromagnetic force. So these are the main building blocks that we have. You can see that they're very, very small. This is essentially 1 over Avogadro's number grams. So it's a vanishingly small mass. So these are the particles we'll be dealing with. You could ask, well, how do we know that the electron has negative charge and the proton has positive charge? And the answer is, it's arbitrary. It's a completely human nomenclature to say that an electron has negative charge and a proton has positive charge. We could have just easily started from the beginning and said the proton has negative charge and the electron has positive charge. It'd actually make a few formulas a little easier to deal with. The important part is that they have opposite charge. That's the important thing. And it's important that we're consistent throughout. Once we decide that electron has a negative charge, it's got a negative charge for everything. We have to be very consistent on that. So those are the particles that we're dealing with. Now, the structure of an atom, you've seen this many times before, I'm sure, but we'll go over it just one more time. You've got a nucleus in the beginning where all the protons and the neutrons are held together by the strong nuclear force. And the electron is delocalized. It's in a cloud. We'll use quotation marks here for now. We'll talk a lot more about that when we talk about quantum mechanics. It's delocalized over a much larger area. There are probabilities to find the electron over a much larger area than where the nucleus is. And yeah, so Rutherford's experiments throwing alpha particles, which are basically helium nuclei at gold foil, showed that most of them went straight through. It's mostly empty space. And then the electrons, yes, are distributed in the surrounding cloud. The total charge is just going to be the number of protons minus the number of electrons. The number of electrons, therefore, the number of electrons is equal to the number of protons in neutral atoms. So the mass of matter is due almost entirely to the nucleus. Have you seen? There's the same number of protons and electrons, and protons are 2,000 times heavier, and there's a bunch of neutrons as well, usually about the same number of protons, a little bit more. And that small amount of mass, that small volume that's very massive, that is where the mass of a compound is. What gravity is pulling towards it, what slows it down in inertia, or rather what keeps it going in inertia, I should say. The interactions of matter with each other are due almost entirely to the electron cloud, though. It's the interactions of the electrons with each other that means that we can't push against things, that we can't go through it. The electrons do take up all the volume, and they're what provides the interactions that we're dealing with. So it's not that it's mostly empty space, it's that all the mass is concentrated, but the part of the molecule that pushes back is everywhere in the molecule. So the positive charge, you're not really feeling the positive charge, that you're feeling the negative shell around it. But the positive charge still is quite important because the electron clouds are held in place by the protons in the nucleus. The shapes of the electrons are determined by the locations of the protons, as well as the locations of the other electrons. And we'll talk a little more about this when we talk about quantum theory, but that's the basic picture of what's going on. elements. The number of protons, which is also called the atomic number, is usually denoted by Z, the number of neutrons by N, and the mass number, A, is Z plus N. Now that's not the exact mass of the atom, that's the mass number. It labels the different possible masses that a single atom can have. All atoms of a given element have the same number of protons, same Z. We lay, so that's the fundamental identity that it has. The number of protons tells you which element it is. Different isotopes of the same element have different numbers of neutrons. So they have the same number of protons, different number of neutrons. In isotope notation, it looks something like this, where you've got a sodium here, the atomic symbol here, you've got the mass number up here, and you've got the number of protons down there, the atomic number. Now this actually is a little redundant because if Z is 11, it is sodium. That's redundant there, but that's the way the notation is usually written out. Maybe so people don't have to look up a periodic table when they see an isotope written down. Yeah, Z plus N at the top and N at the bottom. So ions, different ions of the same element have different numbers of electrons, but the same number of protons. We have the permanent label, the element, based on the number of protons, because the number of protons is not going to change, barring being in a nuclear reactor or in a stellar explosion. So sodium, a neutral sodium has 11 electrons, 11 protons. A positive sodium ion, a cation, has 10 electrons and 11 protons. So it is an imbalance. It has fewer electrons than it would like. And a sodium anion, sodium minus, has 12 electrons and 11 protons. So we have a little plus or a minus to indicate excess or lack of charge. Of course, lack of charge is the same thing as, low charge means, and a minus means having more electrons. Another example of maybe we should have, made electrons positive charge, but we didn't. So Na minus means too many electrons, more electrons that I'd like to have. Na plus means fewer electrons that we'd like to have neutrally. Argon minus, if you have 11 electrons, that's not sodium. You look at the number of protons, it's Ar minus with 11 electrons and 10 protons. So going over this, it's pretty straightforward. It's just keeping track of protons, neutrons, and electrons. We'll have one question here just for practice. I will give the question and then you can pause for a second while you think about it. So this isotope of selenium is used medically for diagnosis of pancreatic disorders. How many protons, neutrons, and electrons does an atom of it have? Thoughts? All right, coming back. So right there, we know, it says right there in the isotope label that the atomic number is 34. Therefore, it's going to have protons at first. It's going to have 34 protons. It's neutral. There's no plus or minus anywhere, indicating that the number of electrons will be the same. And so the question is, how many neutrons does it have? Well, the 75 is not the number of neutrons, remember. It's the sum of the protons plus neutrons. So we just have to take 75 minus 34 to get 41. So E is the right answer there. Okay, next, which of the following is an ion of chlorine? Same idea. I'm giving you the number of electrons, neutrons, and protons, and you think about which one is an ion of chlorine. I'll pause. All right, so for this, if you don't have the periodic table memorized, who has the periodic table memorized? I don't know. You look up the periodic table and you see that chlorine has an atomic number of 17. Atomic number of 17, that means it's got 17 protons. It's got to be one of these two. Now, if it has the same number of protons as electrons, why then it's not an ion, it's just the neutral element. So therefore, this is going to be the answer, C. The number of neutrons is irrelevant. Whether it's an isotope or not, being an ion is independent of being an isotope. So the correct answer would be C. That is the ion. It's the negative ion of chlorine, negative ion of chlorine because it has an extra electron. All right, so that's the brief segment on atomic structure, which we'll explore a lot more when we talk about quantum theories of the atom.